Hello everybody, welcome to Programming and Data Structure at the Department of Computer Science and Engineering, Indian Institute of Technology, Kharagpur in autumn 2020 semester. In this video lecture, we plan to discuss data structure Q. When I say Q, then the first thing probably which come in your mind is that Q in front of a ticket counter or Q in front of a restaurant or Q in front of some cricket match, ticket counter, etc. So the same thing we'll be discussing here. Now let us start with another example, and that example is a one-way. So irrespective of where you are, so traffic jam is common to you. Now if you consider that is a single lane one-way drive, then the car will move very slowly if there is a traffic jam, and even if there is no traffic jam, then also the movement will be one way. And in the one way, whenever a car enters in that way, so whoever will enter first will exit first, since it is a single lane one way road. And from that point of view, Q can be considered as first in first out, which means the car or the person who is entering first will leave first. In short, this first in first out is also called as the FIFO. So Q data structure is of FIFO behavior. So unlike to stack, if you already have gone through the stack, that is last in first out, or LIFO, in this case it is first in first out or FIFO data structure. So here is another example. If I consider that there is a tunnel and only one person at a time can go inside the tunnel, then the person who will go first will also exit from the tunnel first. In that way also, this is first in first out, that is FIFO data structure, that is Q. Typical operations which are allowed and which are also required for the queue is entering in a queue and going out of the queue. So if you consider entering, and if you consider these two black vertical lines as your single lane one way drive, then the car will enter from this side and car will exit from this side. Now in any instance, if there is a queue or line up of the cars, then the first car which is here will be called as the front, and whenever there is a DQ, means the car will go out of the queue, then that will be the first car. And any car, if it wish to enter, then it is a single way moving this direction, so it will enter at the end or at the rear, and that is called as the NQ. Okay, so in order to have this Q data structure operational, the functions which we need is empty to test whether a queue is empty or not, is full to determine if the queue is of full size used or not. So in is empty case, so this rear and front will be same because there is nothing, no car is in this single lane driveway. In is full case, the road is packed with all the cars, so there is no room for any other car to enter. So that is the is full situation. Now front, as you can see, returns the element at the front of the queue. NQ indicates inserting an element inside the queue, and when it is insertion in queue, you know, whenever there is a line which is also called as the queue in front of a ticket counter also, then I am sure you will not allow anybody to enter in between or to go at the beginning of the ticket counter. So he will be always at the end, so that is at the rear side. And whenever it's a DQ, somebody has purchased the ticket or in front of the jam, so jam is cleared, so the first car which is in front, it will go out, so that is removes the element in the front. Okay. Now to implement the queue, what is required? So first thing, you are thinking probably of an array to store the elements of maximum size. Okay. So you can consider that there is a very large array which can store huge number of elements. So that will be the storage for the elements. Without any loss of generality, throughout this lecture, we will consider that the elements are of integer type, but it can be of floating point, character, or any other data type. Even it can be of structure data type, that you know by this time, but we will restrict for the integer only, and if required we will deviate a little bit, then accordingly I will inform you also. Now apart from the array, you need two integer variables. Basically those are the indexes of the array. So one is required to maintain what is the front, another is required to maintain what is the rear. Okay. Now this is the situation of an instance in a queue. If I assume there are room for 8 elements, and at any instance, so it may be the situation that front is always at the 0th index position of the array and rear is at the third, actually the 4th position starting from 0 of the array. Okay. And this information can be stored in a structure data type, and you can define max size of the array as 100. Okay. And the structure I am defining here is structure for queue. What is the member in the structure queue? First of all, an array is required for the storage, that is queue of max size 100. Now if required, just by changing this 100 to some value, I can have a larger array. Then I need two integer variables to maintain front and rear. So here it is front and rear. So three member variables. One is an array which will store the elements, and two index positions in the same array, one for maintaining the front, another for maintaining the rear. I can optionally include this type def option, type def struct q capital Q, but if you include this one, you see that what is the advantage. So since I am using type def, so now onwards, in order to declare any variable for q or with the data type q, I need to write only q. I did not have to write struct q. So that is a good thing, and I believe you wish to do that one. Now using the same data type struct q, if I wish to enqueue, enqueue means I am entering an element inside the queue. Now taking the analogy in front of the ticket counter, so when one person, a new person joins for collecting the ticket, then where he will go? He will go at the end of the queue. Now this front indicates that he is in front of the ticket counter. So here there is a ticket counter. Now rear indicates as of now this many number of people or persons are in line. So as per our definition, we are storing only the integer values, so the elements will be only the integers. Now if a new person comes in, then where he will stand? He will stand at this position, at this position. Now the last position as of now was here. Now after including or enqueuing a new person, the rear will move from here to here, that is increment rear or array index. So incrementing means it will go from 3 to 4. Okay, so that is enqueuing. Now what will be the dequeuing? It will be from the front side. Okay, so dequeuing means that the person who is at the front, he has finished collecting his ticket, so he will go for train or say flight or say bus for which he is collecting the ticket. So this will go to the next, and when he will go to the next, that means increment the front array index by 1. So when it will be incrementing, then this front will move from here to here. Okay, so that is enqueue and dequeue using array implementation. But by this time, probably you started to note one limitation of this array implementation, and that limitation is that from here, so when I am dequeuing one person, then it will go to the next. And in real life situation, what happens that if somebody purchases the ticket and he will go out, then the next person will step in to his place and the next person to his place. That way they will keep on moving and the line moves. But you know, it is an array implementation, and in this array implementation, so unless otherwise I have a separate function to move after the dequeue operation, then the physical movement is not automatic. That way what will happen, this front after the dequeue will go to the end, and if new person used to come, then it will come and it will keep on adding, and definitely the size of this queue is limited. If not, then after some time you may feel that as if all the array is at your disposal, but you cannot able to admit a new person because your front has reached to this position. But you cannot force the front to come at the beginning without moving the elements, because if you do that one, then the queue structure will be lost. And if you do the movement, then that is an additional cost in queuing structure. Okay, so how to deal those things we will discuss. So here we put that one, the problem with array implementation. The size of the queue depends on the number and order of enqueue and dequeue, and it may be situation where memory is available but enqueue is not possible. That thing I mentioned, you can also think of the real life situation. Say if in front of the ticket counter, so it is not a fixed ticket counter, but somebody is there who is actually selling the ticket, and he is giving it to the front person, and after getting the ticket, front person leaves. Then the person himself will come to the next person. You note the front counter or front index is moving to the next person. Then he sells the ticket to the second person goes, then the ticket seller, the front pointer or front index is going to the next. That way, so the list will be exhausted. And if the list is exhausted, then you wish to enqueue somebody, and you see that a huge amount of space is there for the line, but you cannot accommodate that one because the ticket seller has reached to the end. Okay, and that will happen because of the enqueue and dequeue, and definitely it will depend upon the order of enqueue and dequeue. Okay, so pictorially the situation will be like this. So because of one dequeue, front will move from here to next, and because of the one enqueue, this rear will move from here to next. That way it will keep on moving, and finally it both say front and rear will reach here. You will see that this much space is available, but you cannot able to enqueue in that region. What is the solution? If it is possible that okay, so rear will keep on enqueuing, and after reaching this position, somehow rear will go back to this position, then I can use this entire loop until it is filled with the same number of elements as is supported by the size of the array. So in this case, if I assume the size of my array is 100, then it will help me to store 100 elements. If I will reach to the end, then somehow if I go and start from the beginning, then it is possible that you can consider, okay, there is a fixed length of lines. The ticket seller starts from the front, go to the next, and when he will reach to the next, then he is supposed to come back at the beginning. Now if I assume there is one more assistant to the ticket seller who is actually responsible for maintaining the line, so that once a new person will join, he will allow him to fall in line at the end. So that person is maintaining the rear and ticket seller is maintaining the front. So the person who is maintaining the line, when he will find that, okay, so at the end I have reached, say, to some wall or to some boundary, after that one nobody can stand, then that person will come at the beginning and start allocating again. Then the ticket seller will also have the knowledge, after reaching to the end, when he will find that his assistant, the linesman or the person who is actually creating the line, is not standing there, which means he probably has started from the beginning. So ticket seller will also go at the beginning and he will start from there. Okay, so that is kind of a cycle or kind of a circle. So we are moving on to circular array indexing. Okay, if you look at the implementation of the circular array, then you will see that it is very simple. Only thing what you have to do is that even for a static allocation of the memory, you have to use the modulus operation. Okay, so if the size of my array is n, then always the array and front will keep on incrementing by 1, and when it is a linear, then it is just incrementing. Say when dequeuing is there, then front is moving from here to here, which means front is incremented by 1 index position, and when there is a enqueuing, then rear is incremented from here to here, that is increment of the index by 1 position. In both the cases, just increment was there. In circular array concept, physically it will be simple like this, but during the implementation, what we will do, we will increment and then take the modulus by the size of the array. Okay, so if that is the situation, then what will happen for this rear? So when rear will reach to this position, that you can consider, say, as the nth position. Now if I wish to enqueue one more person, say I see that one more person has come, then I will increment this one, then that will be n plus 1 mod of n, so that will give you the remainder as 1. So rear will come here and it will start storing that one. But when to stop? When rear will find that I am reaching to front, then I will stop. Okay, and when front will stop, when front will reach to rear, then it will see that there is no more person, so you stop. So that is the simplest implementation using the circular array. There is another solution also using linked list. I will go to that one later. So let us first elaborate on circular arrays. So here is a circular array with index position shows as 0, 1, 2, 3, 4, 5, 6, 7. So initial position is front 0, rear 0. Since front equals to rear, so I understand that no elements are there. Now if I assume 4 elements are entered or enqueued, then what will happen? Front is here at the 0th position, but the rear will go at the 4th position. So front is 0 and rear is 4. So after inserting, actual term is actually after enqueuing A, B, C, D, like this way. Now if I delete or if I dequeue, the correct term is dequeue, A and B, which means from front A will go, B will go, so front will be 2 now. So front is standing here, 3 and 4 is filled with the element after the deletion of this A and B. Okay, now you see that front will keep on moving and it will be filled, or the queue will be full only when all the elements are available there. And that is, you know, that if that is the situation, then there is only one solution: you increase the size of the array. Otherwise I cannot solve that one. Okay, so here is how you should calculate front and rear. So front index of queue head always empty, that I will assume. Rear index of last element unless rear equals to front. So here this equals to is the comparison operator, it is not assignment operator. Okay, but you know, in English or in literature this indicates comparison operator. Since this is not part of the C syntax, so it is not double equals to. So front is 0, rear is 0 and queue is empty. Now when front is 4, rear is 3, then queue is full. Now how to check whether queue is empty or not? When front equals to rear. And how to check whether queue full condition is there or not? Front equals to rear plus 1 modulus max queue size. This max queue size is same as the dimension of the array. And you see this modulus operation. So, and also one element is free, that to keep track that front and rear is separated, and using these two conditions separately we can identify that whether queue is empty or full. So this is a small data structure definition. Okay, so in structure definition, for creating and initializing a circular queue, again I am defining the maximum size of the array as 100. Now type def using struct in key. This is just an example, but you can have other name also, and I am mentioning that as element. Now this is the queue definition, structure definition. Type def struct element list max queue size in front and rear. These two indices are required to maintain the queue, and the name of the data structure I am defining is queue. Then I am creating one queue variable, that is small q as capital Q, and where q dot front equals to 0 and q dot rear equals to 0, and that is the initialization. In the last slide, if you allow me to go back, I mentioned that here front 0, rear 0 and front equals to rear, that is the empty condition. So here q dot front equals to 0, q dot rear equals to 0 and q dot front equals to q dot rear. So that is my initialization, and that is the status when q is empty. Now in order to check q is empty, I will check front equals to rear. Now this arrow operator you are introduced with during the structure indirection, so pointer to the structure you are introduced with this one. So you understand that indicates actually the element of the q data type front and rear. When they are equal, then I am returning 1, indicating that yes, q is empty, otherwise I will return 0. Useful condition is if front equals to rear plus 1. So you remember that example, there is one difference. So front is at 4, rear is at 3. Now if I add with the rear one more, 3 plus 1 4, so with that if I take the modulus, then it will be equals to the front. Then I will declare yes, the queue is full, return 1. So I cannot accommodate any new entry until there is a DQ operation. But whenever there is a DQ operation, I can make a new NQ operation, which is not possible for single array without this circular implementation. Now element front that you will get using this queue list, queue front plus 1 modulus max queue size. For NQing, what you need to do, rear is advanced by 1, increment the rear, and after incrementing, since it's circular, so I am taking the modulus. After taking the modulus, what is the value is stored in queue rear, and that is the index of the queue rear in the queue list, and element is entered there. Okay. For the DQ, what I need to do, that queue front plus 1 modulus max queue size will be assigned to queue front. But you know that for DQ you need to print the value, then perhaps you will print first and after that one you do the DQ. Print or you return that particular value after reading from the queue front. So after reading from queue list in the square bracket queue front, after reading that one, storing that one in local variable, then you advance this one. So after advancing this one, either you can return from this DQ or you can print, or you can do whatever is required to do after DQing operation. Now here is a demonstration of queue using linked list. So you are introduced with the linked list, and in the simplest case you can assume the existence of one element and one pointer variable. Okay, so pointer will point to the next node in the linked list and the element will be stored there. And as I mentioned, we can assume that the element is integer, but there may be other elements also which is allowed. Now the problem we have faced in single array implementation is that array is available but NQ is not possible because I reach to the end of the array. So that problem has been handled by implementing the single array using circular representation. Then that problem was solved. Still the problem remains. Initially if I declare, say, the size of the array, which is also the maximum capacity of the queue to house the number of elements is 100, then if I have more than that, then it is a problem for me. And you have seen that in many cases linked list can be a great savior when the situation is limited because of the array implementation. There is also application of linked list in queue, and in this case also linked list will appear as a savior. So create a linked list to which items would be added to one end and deleted from other end. Two pointers will be maintained, one pointing to the beginning of the list, point from where element will be deleted or added, another pointer to the end of the list, point where new elements will be inserted. So this is an instance of a linked list you are familiar with. Okay, so this is the head node you can consider, and this is the end node, and since it is an end node, so it is pointing to nothing, so I am grounded it, indicating the pointer of this node is null. Okay, now I am giving two pointer, one is front, another is rear. Okay, now we will also demonstrate that here this front or rear is actually auxiliary. I mean that this can be front, this can be front, and this can be rear also. So I will go to that, but before, if this is front and this is rear, then you understand if I wish to do NQ, so that NQ will be done at this end. Okay, so I have to traverse the whole linked list. I will reach here, then I will connect with the new node, and the rear will be the last one. Okay, now if I wish to DQ, then DQ will be easy. So this pointer variable from here will move out, and this front will be this one, and this will be DQ'd. So in this case, in this implementation, when front is at the head node and rear is at the end node, then DQing can be done by just one simple operation, that you change this front from here to here. That's it. But for NQing, you have to traverse the whole list. On the other hand, if your situation is rear is at the head node and front is at the end node, then for NQing you have to add only one element here, and then you take the pointer here, and for DQing you have to traverse the whole list. Standing at this position, you declare that this is my null and you free this memory. That's it. Both are possible. Okay, we will show both. So first, NQing option, and in this case NQing will be done at the end, because as per my assumption rear is here and this is my front. Okay, so what I need to do? First, I need to get one node. I will copy the content there, and after copying that content, so what I will do? I will make the pointer for this node as null. So I will ground this one. After grounding this one, what I will do, that I will change the pointer, this one of the last node, which is currently rear, so that it will point to this one. Okay, since I created this new node, so its address was returned and stored by me, so I will store that address here, or override that address here on top of null. Then the connection will be established here. Now the address is known to me, through which I have added this one. So the rear will pointing instead of here to here. Okay, now this is my new list, and here NQing is done at the rear. Okay, now for DQing operation in the linked list, when front is at the head node and rear is at the end node, so DQing means I have to DQ it. So after reading the content, if I need that content or printing that content, what I will do? I will just increment this pointer from here to here. So this will be my head node as well as the front node. So this is very simple. I will remove this pointer, or I will superpose the address of this one by this one. So the address of this one is stored in this pointer. So the content will be given to front as well as head. If I wish, then it will point here. Now that's it. That's not all. Since I am DQing and this node is very much there, so it is my responsibility to free the node using the free function. Otherwise, it will create some dangling pointer. And if I keep on NQing, DQing, then after certain time I will find the memory is limited and I cannot enter a new node again. So these are the functions which can be implemented in queue, which is basically first in, first out, or FIFO structure. You assume queue contains integer elements. So void in queue, so q star q, what is the q? The data structure we declared, integer element. It will insert an element in the queue. DQ, it will remove an element from the queue. Now create queue, it will create a new queue by creating two pointers. One is the rear, another is the front. So in the context of linked list, pointer is known to you, but if it is array, then it will be index. In both the cases, since it is pointing to some position, so I am calling that as a pointer. Okay. Now int is empty q star q is to know the status of the q, whether it is empty or not. Int size q star q will able to help you to know that currently what is the size of the q. There is another interesting function which can be operated on q, that is int peak q. In this case you will read the value or read the element, but you will not basically dequeue this one. So in dequeue it is reading as well as removing the element. In case of peak it is just reading but not removing the element. Okay. So combining all those things, if I write that one as functions, then I can consider the q is kind of a black box to me, where enqueue, dequeue, create, is empty, size, all will be acted as a function on that black box, and that's why it is abstract to me, or also called as the ADT, abstract data type. So the data structure for q using linked list may be looking like this. First, I am defining one node, that is simple, similar to any linked list node creation. One space for or one element is value, another is struct q node star next for the pointer for this particular node. Then I am creating struct q as struct q node star q front star q rear, and type def struct q as capital Q, so that whenever I will create one variable of data type q, then I will have q front, q rear inside, and also I will have value inside that one. Okay. Now this is an example of enqueue. Please do not be confused. In the previous example, when we discussed, the enqueuing was done at the end, at the rear, you remember, and also at that time I demonstrated that enqueuing can be done at the beginning. So it is basically depends upon the programmer and its convention. If it is say at the beginning, enqueuing or dequeuing, so whatever is at the beginning, so that will be less time consuming compared to whatever is at the end, that you understand. But in this case, enqueuing is done at the beginning, and when it is done at the beginning, then you see that struct q node star q1, q1 equals to struct q node star malloc size of struct q node. This is the standard statement to generate or to create one q node structure. Okay. After creating that one, I am copying the element inside the value of that one, q1 value. Then I am copying the address of the q front to the next. So in this case, the front, in this case, the head node is considered as the front. Okay. So since head node is considered as the front, then what will happen, that in the head node I will copy the address of that one. So again, what I wish to say, that I will create one q node, and after creating the q node, inside that q node I will copy the element. After copying the element inside that one, then the pointer or address of the q node will go to the q front. So when it will go to the q front, then it will connect it to that one, and I will go to the beginning. So this q front indicates the head node, and that way I can enqueue. Now in case of dequeue, okay, before that one there is size function. So let us discuss this size. So size is simple. So I have to traverse the whole queue, and while traversing the whole queue, then basically I will keep on count. So I am starting with q1 equals to q. I declared one variable q1. I am copying the q which is passed to me, and then I am initializing int count equals to 0. Then while q1 not equals to null, then q1 equals to q next count plus plus, that way I am doing. So I am going to the next queue, and I am going to the next node. I am incrementing the count. That way I am keep on incrementing the count. Then I will finally return the count, and that will give me the size. This is very straightforward. Now peak will actually give me the value but will not dequeue. Since I am interested about the value, but I do not interested to delete that one, okay, or dequeue that one, then what I will do, that I will traverse the list starting from the beginning. So beginning will be copied from star queue to q1. Then using q1 I will keep on traversing until I will reach to the node whose next is null. Now if the next of that queue node is null, then I know this is the last node. So that is the node where actually front is. Front as per the queue structure. So from there dequeue will happen, but I will not do the dequeue because it is peak. So what I will do, I will return the value only. So q1 value will be returned. Okay. Now if it is a dequeue, then the same thing, not same actually, similar thing like the peak, but for dequeue only the value is not required, but I have to delete that node also. In order to delete that node, so I will have two nodes. One is q1 star q1 or pointer, and another star previous. Now q1 equals to q, while q1 not equals next not equals to null, I will traverse. But you see that there are two pointers. One is this one, another is this one. So from your side, so if I assume that this one is going to the end and this is following, so if this declares, okay, I reach to a node whose next is null, which means it is the last node, then I am just before that one, because what previous is taking? Previous is taking q1 and q1 is advancing after that one. So previous is following q1 and just one step before the q1. That way when q1 will reach to the last node, then previous is just before that one. So q1 when will return its value, that is the value of the front index position or front position of the queue, but the previous is just before that one. So after returning the value from there, what I can do, that this q1 is no more required. I am dequeuing that one. So what I will do, I will make the next pointer of previous, which is currently pointing to the last node, as null. The moment I will do it null, then what will happen? The link is established from the beginning up to the previous, which is penultimate one. So before the last. If that is the situation, then q1 is now dangling, means there is no connection, but q1 itself contains the address of that one. Using that one, what I will do, I will free this. So I am reading the value from q1 val, I am putting previous next as null, so ending or chopping it out, dequeuing operation. Do not stop here, do not stop here. After this one, what you need to do, free q1. So it is your responsibility to free that one. Okay, so all the memory locations which are dynamically allocated must be freed, otherwise there may be some memory leakage problem. So the applications of queues are like waiting lists, access to shared resources, for example printer, multi-programming, and these are the direct applications. And among the indirect applications, auxiliary data structure for algorithms, component of other data structures are there. Here is an example to print fast n Fibonacci numbers using a queue. Initially, you assume that the front is having 0 and rear is having 1. Now you keep on adding one more location, and then you know that basically this location will be the sum of this location. That way you keep on adding that one, and then you do that one. Okay, so please implement this one. Next example, or you can consider exercise, is use a stack to reverse a queue. This is pretty simple. What you have to do, that this is my initial queue. Okay, so if it is initial queue, so 14 is at the front, then 18, then -5, and at the rear is 30. Now I am using a stack. So this is my stack. Now you know the stack operation, only push and pop, and there is only one pointer, that is the stack top. Now if I dequeue from this queue, then 14 will be dequeued, then I push it to the stack and it will go here. Then I dequeue this and it will go to here by push. So one dequeue from this queue and followed by one push inside the stack. That way -5 will go here and then 30 will go here. Now you know that stack, unlike to queue, is a LIFO structure. So it is last in first out. So whoever has gone last will come out first, because it is also pointed by the top. So the top will output 30 first. After outputting 30, it will be placed here, and that will be the front being the first element. Then I will pop, then -5 will come here next to the front, then 18 will come here, then 14 will come here. Now compare with the initial queue structure and the final queue structure, you see that it is reversed. So by the queue, by the help of one stack, I am basically reversing the queue. And the operations, what I am doing, that dequeue, push, dequeue, push, dequeue, push until the queue is empty, assuming the stack has the enough space to accommodate all the elements of the queue. So I am not testing whether stack is full or not. Okay, and after that one, what I will do, that pop from the stack, pop in queue, pop in queue, pop in queue, and I will keep on going until the stack is empty. Well, for that first thing, probably I have to check that before we start the process, the stack is empty. So stack is empty, stack operation returns yes, and I assume that the stack has the enough space to accommodate all the elements from the queue. Okay, so that's it. If it is, then by doing dequeue push, and when the queue is empty, then pop in queue, pop in queue, and when stack is empty, I am done. Okay, now I believe you can implement this one also. Now here it is a problem on create a new queue with given elements appended at the end of the queue in a reverse order. So what is done here, you see that this is my front and this is my rear. 4 elements are there. Now what I am doing, along with that one, this 30 is appended, -5 is added, 18 is added, 14 is added. So that way I am adding that one. Okay, so given this as input, you need to output this one. So this is a queue, this is also a queue. Now what is there? The same queue is appended by the reverse value. So you can use a stack in order to achieve the outcome. Okay, that is the hint. So just to give you more hints so that you can implement, in the previous slide I demonstrated how to use a stack in order to reverse the queue. Right, now during the reversing, so if I do not reverse it using the dequeue, rather if I use the pick, so what pick will do? Pick will actually read the value but will not remove the value from the queue. So if I use pick and use stack to store the picked value, then it will be post in, and when the all the read is done, then what I will do, I will pop an NQ. So then NQ will go which way? Okay, you have to think now. Okay, so you solve that one using a stack. Okay, so that is the hint. but I am not giving you the solution. That you have to do. Now implement a stack using a queue data structure. Okay, so for a given stack, create a same size array which you are going to use as a queue. Push and pop operation of stacks should be emulated with the enqueue and dequeue operation. You can use an intermediate queue for the above implementation if required. So as a homework, you can consider the implementation of a priority queue. This is very important one, which maintains the items in an order ascending or descending and has additional functions like remove max and remove min. And also a separate homework problem to you is implement to maintain a doctor's appointment list. Okay. So that's it from the queue part. Okay, thank you very much.